Hello and welcome to week 11. In this section, we're going to learn about chi-square tests. And in particular about chi-square tests, we're going to learn about how to analyze categorical data, which is really important in the health sciences. So with that, we'll start by understanding what the tests are, how they work, the assumptions that we use them by, and how we can apply them in healthcare examples. So if you don't remember what a categorical or parametric versus non-parametric tests, thus far in the semester, we've been looking at mostly parametric tests, that is continuous data. And now we're going to look at these non-parametric tests where the data isn't continuous. They're usually categorical. Something's either on or it's off, okay? Or you get a positive or a negative, okay? So those are the non-parametric tests. And so we're going to look at those. We're going to again look at it in health care data analysis and compare observed versus expected frequencies. So there are two different types of chi-square tests. So the first is a test to look at whether or not data is independent. So we've previously talked about independence, right? Are the two populations somehow related or dependent on each other? So for example, whether the smoking status of a patient is tied to the presence of a chronic disease. And then the second is what we call the goodness of fit. This is the one that I've used the most when I've used chi-square, and that compares one categorical variable in your sample to a known or expected distribution. And so it's kind of like comparing blood types in a clinic to the general population blood types. So thinking about these two hypotheses really quickly, or types of chi-squared tests, we need to think about how that influences our hypotheses. So let's talk about the null hypothesis first. And of course, we understand previously that the null hypothesis means no effect, right? So in this case, we're just going to word that in a way that works with our understanding of the two chi-squared tests. So in this case, there's no association, or there's no no association between the two populations, or there's no match in the populations for the two types of chi-square test. Alternatively, our alternative hypothesis would be that there is an association, and there is a mismatch from what is expected. So remember, in the second type of the goodness of fit chi-square test, we're looking at whether or not the population is the same. We're comparing it with the observed or an expected value, okay? And we suspect that there is a difference in the alternative hypothesis, a mismatch, okay? All right, so I hope that's helpful. All right, so what are the assumptions when it comes to chi-square tests? First of all, obviously we need it to be categorical data, and that category data needs to usually be frequency counts, okay? Independent observations, obviously. One of the nice things about the chi-square is it does its own independency test, so that's really nice. The other kind of interesting thing is that frequencies need to at least obviously be greater than or 1 or greater, which makes sense, right? You're not going to have a frequency of less than 1. And then 80% of your your frequencies need to be greater than or equal to 5. And that is simply because the chi-square test just doesn't work as well when the frequencies are, there's too many frequencies below 5. And there's a risk of type 1 and type 2 errors. Remember, type 1 is falsely rejecting the null hypothesis, and type 2 is failing to reject a false null hypothesis. So just remember that you want at least 80% of your counts to your counts to be greater than equal to or greater than 5. Yeah. And then, of course, with that, you need to have a sufficient sample size, and hopefully they're random as well. Now, what happens if you violate these? There are other tests that you can use, one called the Fisher's exact test. You can use a collapsing categories test, a Monte Carlo simulation, which we haven't learned in this class, but there are always ways to go around the fact that we can't use the test that we would like to use. So the chi-square test gives you a formula. All right, so this is what our chi-squared is. It's kind of an x, fancy x squared. And what we do is we're going to take the sum of what is observed minus the expected, and we're going to square that and divide it by the expected. And so you're comparing all the data to the observed versus the expected, okay? All right, so we also need to know the degrees of freedom as an important part of these tests. So if we're interested in the test for independence, we're looking for the number of categories. In this case, down here, we've got 4 categories, right? For the different blood types. And, oh, sorry, that's for the goodness of fit. So let me talk about the goodness of fit, although we'll need that as well. So I'll start with the goodness of fit real quick. So K is equal to the number of categories, 1, 2, 3, 4, right? So that's 4 categories. So K minus 1 would be 3. And that would be the degrees of freedom for the goodness of fit. Now, the test of independence, you've got R and you've got K that you need to know about. R is the number of rows. So again, 1, 2, 3, 4. So 4 minus 1 is 3. Okay. And then C is the number of columns. So 2 in this case, being male and female. 2 minus 1 is 2. So we got 3 times 1, and that would give you still give you 3 degrees of freedom for the test for independence. So how do we interpret a chi-square test? So the larger the chi-square, the larger you expect there to be a difference between the observed and the expected value, okay? And the smaller means that the observed data fits the expected pretty well. And then you're going to get a p-value, and that will help you once again to assess the significance of the chi-square. So let's look at this in Jamovi. And so you can see that we've got a data set here, smokers versus non-smokers, and whether or not they have heart disease. Again, it's categorical. And so we're going to need frequencies. So we're going to use this button over here in frequencies, and we've got a few things to choose from. All right, so what we're going to do is we're going to select independent samples from this frequency menu here. So we've selected that, and then we're going to move the smoking status over here into our rows, and heart disease over here into our columns. And automatically that's going to generate a table for us. So all right, so we've got our chi-square test and our table. We checked our hypothesis. Group 1 is not the same as group 2. There's a mismatch. So we're good there. And so what does that mean? How would we summarize, explain that a little bit? So just real quickly. So if we wanted to look at the expected values, we could scroll down here and click on cells and click on expected, right? And if I move myself up here, you can see there's our expected values right there. I'm sorry, expected right here, expected right here, which is important if you're calculating all of this by hand. We would do each of these columns by taking 75 minus 50 and then squaring that. And then come down here and doing the same for each one of these values here. So we would do it 4 times that same thing. So in this case, it would be the observed minus the expected divided by the expected, or sorry, let me just show you what that looks like. So this is going to give us chi-squared here. And so in order to get the chi-squared, we're looking at each one of those 75 minus 50 squared divided by 50, 25 minus 50 squared divided by 50, and then 25 minus 50 squared divided by 50, and the last one. And of course, this gives us our 50 chi-square, which in our chi-squared table, we get 50 right there, right? So observed and expected, those were our 2 values that we just saw in those formulas. And so that shows us basically how we could have got those numbers, okay? So because the p-value is 0.001, we can reject our null hypothesis. There's definitely a mismatch going on there, or we've got evidence that suggests our alternative hypothesis is correct. So our conclusion is that the statistically significant relationships between smoking and heart disease in this particular sample. There is a relationship. Whereas if there was not a significant difference, we would say that we don't have a good, any significant relationship showing up between smoking and heart disease. But that's not the case. What we found was that there is. So something that could be also helpful when we're doing this is understanding how big that effect size is. And so what we've got is this Kramer's V that allows us to do that. And you can see the formula there. And it's going to measure the strength of that association. And so if we had a small number between 0 and 1, like 0.02 or less than 0.02, we would say that's small, not a very strong effect. Medium would be 0.3 to 0.5, and anything above 0.6 would be stronger effect size. All right, so how do we look at that in terms of our contingency table? Well, look right down here under nominal, under statistics, under nominal, we got filling Kramer's V. We're going to click on that and just move us down and my face over. You can see that the Kramer V is 0.5, and we learned previously that the 0.5 is a medium effect size. So we now know what that effect size is. So in summary and translation, chi-square tests analyze categorical data. It's a test used to test the independence for association. We use it for a goodness of fit, which we are going to look at. And next, on Wednesday, you're going to learn how to apply the test of independence in some more healthcare data.